Okay.
Okay.
So this paper has been published in IEEE Access, Volume 8, on the 3rd of December 2020. The paper title is ResNet LSTM for real-time PM 2.5 and PM 10 estimation using sequential smartphone images. This paper is by Shiguan Song, Jacqueline Lam, Yang Hang, and Victor O.K. Lee from the University of Hong Kong, Hong Kong. So this paper is basically concerning PM 2.5 and PM 10. PM 2.5 is the atmospheric particulate matter having a diameter less than 2.5 micrometers, and PM 10 having a diameter less than 10 micrometers. Both PM 2.5 and PM 10 have presented great public health challenges given their devastating health impacts for those living in higher level pollution areas. And both PM 2.5 and PM 10 are detrimental to the environment and present tremendous health risks to the public, especially for those who are suffering from respiratory diseases, the elderly, and the young children. These both particulate matters can be easily inhaled into the lung and absorbed by the alveoli directly. Are the small tubes inside the lungs which exchange the oxygen and the carbon dioxide. Hence, it can affect the respiratory and the cardiovascular system and trigger asthma attacks, respiratory inflammations, and even cancers. So it is important to take the readings throughout the city and make it publicly available to any citizens who plan to have their outdoor activities. The challenges faced right now are because of the government run air quality measuring stations. They are quite expensive and very limited in number, so they are not available everywhere. People residing in areas where AQMS are the air quality measuring systems, can only rely on the readings from the nearest AQMS, which might be far away. And not everyone can afford their own personal PM sensors too. So many researchers have taken part in like developing own PM apps in which PM 2.5 estimation is done. These are basically done using feature-based machine learning models like support vector regression. And basically these models, they extract the features of the images, the contrast, the saturation, and then try to understand the degree of PM values. These models are highly dependent on features which are constructed, and their performance can be easily distorted by any change in the environmental conditions. Uh, Excuse me, should I go slow or fast, or is this okay to understand?
Yes, it's okay.
Okay,
I can.
okay, okay. These, while learning these images, these features are manually selected for the air pollution estimation, and the conventional machine learning methods can be less robust compared to the deep learning methods, which extract image features automatically. Some studies have used deep learning models to improve image estimation, accuracy, and performance. But here also we face problem of the degradation which happens, the radiant degradation. So although deep learning models have been able to extract image features automatically, these studies have only considered spatial features extracted from single images on CNN models, while temporal correlations of sequential images are ignored. Temporal correlations are the images which come from the same background, the same area, but at different time. And this happens because CNN models can only learn features from single images, but not how images change from one temporal instance to the next. And the recurrent patterns such as daytime versus nighttime images, they are ignored. So basically in this particular research, focus has been made on understanding the temporal correlations also, and also taking care of the degradation which occurs. So to improve the image quality, to improve the quality of the image-based PM estimation using nighttime images and end-to-end ResNet LSTM model is proposed in this study. The proposed model can estimate both PM 2.5 and PM 10 values directly from the pictures taken by the smartphones. It achieves lower estimation errors and possesses high pollutant estimation capability after incorporating both daytime and nighttime images when compared to the other baselines such as the CNN baseline models, the previous ones which were developed. The novelties of this study are as follows. A temporal fine-grained image set is constructed with corresponding PM 2.5 and PM 10 values which are labeled on the images. 3,024 images have been taken consecutively in a time sequential order at the Cyberport Waterfront Park in Hong Kong, covering both daytime and nighttime images. And end-to-end, the second novelty is an end-to-end ResNet LSTM model using sequential images as inputs is constructed and achieves the best PM 2.5 and PM 10 estimation when compared to the state-of-the-art baselines. ResNet LSTM also incorporates sequential images taken every minute for estimation of PM 2.5 and PM 10 values for a specific location to enhance the robustness. It is the first deep learning model used to estimate the PM levels which are based on nighttime images. A novel MET is meteorological, ResNet LSTM model is developed based on newly developed ResNet LSTM model, taking into account 6 meteorological features. These meteorological features are temperature, pressure, humidity, UV index, sky covered, and precipitation. In addition to so they have taken the meteorological features into account, which also gives a better performance when compared to the RSTM, ResNet LSTM model. So a new model, ResNet LSTM SP and MET ResNet LSTM SP are constructed. SP stands for short path, are constructed to improve the estimation performance by comparing the results of each and that of the ResNet LSTM and MET ResNet LSTM. So the methodology behind this research is first, air quality sensors are calibrated with reference to the instruments of the official air quality monitoring stations located in Hong Kong. An experimental study was conducted to verify the PM 2.5 values and the PM 10 values and obtain high accuracy calibration with portable sensors, high accuracy with calibrated portable sensors remaining constant with a radius of 500 meters. So the values were taken from 0 meters, 50 meters, 100 meters, up to 500 meters. And it is, what do you say, made sure that the PM levels are constant during this meters, during this radius. So hence, the learning is better. If they are not constant, then the learning and the images would vary, which we don't want. Around 3024 outdoor daytime and nighttime images are taken of the same building with a radius of 5 meters, labeled with corresponding PM values using co-located calibrated high accuracy sensors. The collected data was then pre-processed. ResNet LSTM was refined by incorporating meteorological features and one short path to exploit the fullest potential of ResNet LSTM for PM 2.5 and PM 10 pollutant estimation. So if you see in the figure, we have the sensors, we have the calibration done. Then daytime and nighttime images are collected at 1 minute's distance, 1 minute's time frame. The meteorological features like temperature, humidity, pressure, UV index, sky covered, precipitation, all are added. And all these inputs are given to these two networks. In one network, the meteorological features are not added. In this network, in this particular block, the meteorological features are added. So here the images are given as input. Here the meteorological features are given as input. The images are given as input to the ResNet convolutional network, which is given to LSTM, and then everything is added to get the PM value. The image data augmentation is done by taking the same image and rotating it horizontally vertically, and we do this because the PM values in the image are constant. So to reduce the overfitting and improve estimation performance, the smartphone images have been augmented before being used to train the model parameters. While training, the images are resized to 224 to 224 to couple with the input dimensions of the ResNet. Because of this augmentation, the size of the data set increases, but also it improves the estimation stability. These images should give the same PM values as it's the same image while being rotated, flipped. Now we come to the residual network which is being used here. The deep convolutional network, CNN, can extract different levels of spatial features from the images by stacking more network layers. But when we do this, it is found difficult to train the deep CNN model based on observation that the network depth increases. Training accuracy, because of the increase in the network depth, the training accuracy gets saturated and then it starts to degrade rapidly because of radiant degradation. To overcome the degradation, a deep residual network was proposed to facilitate the training of the deep CNN models. So in this residual network, the deep residual network addresses the issue of degradation by adding an identity mapping. This is the identity mapping which is added as represented by the curved line. So here X is the input layer, H is the desired mapping function, Fx is the residual mapping function. During the training, the problem of learning the desired mapping function Hx can be reformulated and it's the learning the residual mapping function Fx. So Fx is equal to Hx minus X with an explicit reference to the layer of inputs. The original mapping function Hx then becomes Fx plus X. So the issue of degradation out here is does not happen because we have the original features also added to the output of the system. So if we see here in the residual network, okay, this ResNet 18, it consists of 18 layers, which is implemented to deeply extract the spatial features of our images with the aim to address the degradation problem. Because of the connections between the each convolutions, the degradation problem is avoided. The last layer of the ResNet is modified to provide a single output. This is the last layer, is modified to provide a single output to give 512 vector reading, 512 size of the vector. The images are first read by the system and resized to the input dimension of 224 by 224 by 3 channels. These are corresponding to the RGB channels. The width and the height of both the images are 224. After average pooling, in the last convolutional layer, the images are converted to a flattened vector with a size of 512, which is passed to a fully connected layer, and the PM 2.510 value of the images are then estimated. The size of the output of the last fully connected layer is changed to 1 to represent the final estimated values for PM 2.5 or PM 10 estimation. The parameters of the ResNet are updated again by backpropagation. The second, we use long short-term memory. In this long short-term memory, uh, which is a time sequential model, can extract temporal domain features from any sequential data. This basically is used to, sorry, this basically is used to take the images which are again and again fed, and also to process the output of the ResNet. So if we look at this, this is the input gate, this is the input given, and FT is the first gate, the forget gate here, which is updated by the outputs of the, okay, sorry, I'm a bit nervous, sorry. The forget gate is used for controlling the information from the previous cell state. It decides how much information should be kept or on pass to the next state. This is the forget gate. The second gate is the input gate, which decides how much new information should be used. The current state can be updated by combining the output from the forget gate with the input gate. The information in the latest cell and from the input are used to update the latest hidden state. The information from the hidden cells and this thing. And that one, update the latest hidden state. while also serving as the output for the LSTM. The parameters of LSTM are updated through backpropagation. Are there any questions on this?
I have a question. What is X in this paper?
X is the input, the images.
Is it a
Uh,
pixel?
no, it's not the pixel. It is the output of the ResNet network.
Okay, so it is single dimension.
Single
Just one
dimensional.
value.
Yes.
I see.
Yes.
Okay.
Yes. Yes. Yes.
Okay. Thank you.
Yes. So if we see here, the input from the ResNet is given to the LSTM. Now, this image is of the ResNet LSTM with one short path. The first 10 consecutive images are taken every single minute, and the previous 9 minutes are fed into the ResNet model. Then the 10 corresponding outputs of the same ResNet model are fed into the LSTM model subsequently. In order to match the output of the ResNet, the input size and the hidden layer units of the LSTM model were set as 512. The output of the vector is 512 of the ResNet, so hence they were set at 512. The final hidden state of the LSTM model is used to predict the PM 2.5 or PM 10 values via fully connected layer. But this particular model does not take the meteorological features into account, and hence, by adding the meteorological features, we get better estimation of the PM value, which is done in this block diagram. This consists of the proposed ResNet LSTM model of a parallel LSTM model. For the parallel LSTM model, 6 meteorological features observed at every single minute real time and the previous 9 minutes were used as input. The two final hidden states from the ResNet LSTM model and the parallel LSTM model were concatenated and used to estimate the PM 2.5 PM 10 values by a fully connected layer. So from here, the input of the meteorological parameters are given. From here, the input of the images are given. And then by connecting these short paths, the PM values are estimated. So this gives the input dimensions and the output dimensions of each part of this model. Here, FC is the FC stands for fully connected. R stands for ResNet. L stands for LSTM. M stands for meteorological input, and SP stands for short path.
Sorry, Anupam.
Yes.
May I have a big question? So
Yes.
that you mentioned before, this research have around 2,000 image, right?
3024 images. Yes. Yes.
Something like
Yes.
that.
Yes.
So you can describe for more detail how do they input for this system, something like that. Why they use only that they mentioned in the research, just like 3,000 image. That enough? Is it enough for
No,
create image?
it is not enough because these images were taken for from a particular area. In the research approach, means like in the future work of these images of the projects, means like to improve the whole, more images are going to be taken. But like if we see here, limitations. In the limitations, no, future work. So this particular estimation is done only for that particular area in Hong Kong, and it is enough for that area. But if you want to increase it, if you want to make it more acceptable everywhere and this system to run everywhere, then more sets are going to be taken. And the 3000 sets which are there, of which 70% is used for training,
I see.
10% for validation, and 20% for testing.
Mm-hmm.
Anything? Any more questions?
Mm-hmm. Are they divided?
Are they? Yeah. Yeah.
Sorry,
Yes.
actually, I have some confusion about the image. Why they
Okay.
need image? What they want to interpret the image for what?
The feature extractions of the image.
Yeah, I know they need feature extraction, but what kind of data that they need from the image?
Uh, the the pixels which have been because okay, I'll just okay, 1 second. In this, is there any image out here? 1 second. So in this image, the contrast and the saturation of this particular image is taken into account. And that is compared with the actual PM values at different PM values to understand the differentiation because of the light scattering.
Mhm. So how they know they use image processing on or they did not use?
They did use image processing.
So what kind of algorithms that they use for image processing that you referenced?
Okay. Uh, so basically, they take the image and convert it to 224 into 224 size, and then each pixel is understood, and in this particular algorithm, the saturation and the contrast of the images is compared and then understood how to go about it.
So they use resident network 18, right?
Yes.
And why they select 18 for the number of the resident network? Why they not use 64 or something else? Because I know that if we prepare resident network ResNet first, right, and then go to
Yes.
the LSTM, normally is the performance will get better if the number of the 18 or 64 node, something like that, is increased, the
Yes,
performance is get better.
but what happens is if you increase, then also the degradation occurs. And in this particular ResNet, in this CNN model, what you're talking about is the RNN model. In RNN model, the more the deeper it goes, the more accurate it becomes. But in a CNN model, these many steps, these many layers are enough to extract the features of the image.
So 18, they use only one less network, right? They did not compare with other, right?
They did compare with others. The previous work, they did compare with the previous work.
But they did not tie in others LessNet, right? Only one LessNet.
They used ResNet because in others, after getting the output, because of the gradient degradation problem, the exact
Yes.
the issue of forgetting, or like the main,
Yeah.
yeah,
They use
that
LessNet.
comes. Yes,
They
so
use
hence
LessNet
they,
because okay.
yeah, hence they used ResNet.
They use LessNet because they want to avoid the vanishing gradients, right?
Yes.
But you use
So
only 18. I mean
yes,
paper use only 18. I think it's
yes,
quite less in my opinion because
yes, but out here the image size also is reduced to 2 to 4.
yeah.
Yeah, if you just increase the layers, instead of 18, if you like use 64 or something else, then the complexity also increases unnecessarily. We don't want to just increase the complexity if we can get the same or the similar accuracy with a
You mean
lesser layers.
overfit, right?
Yes, overfitting is not necessary.
Okay. Okay.ครับ.
Means, am I right, am I wrong?
It's
this,
okay,
this,
but
this, this, this is what I'm thinking.
224 that resolution is quite small, no?
Yes.
But
It is small, but it is enough to extract the features which are needed. If we increase the resolution, then the complexity of the whole algorithm also increases, and it becomes
and
more tedious
I
comparatively.
also did not understand why they use LSTM, why they not implement on CNN or something else, because I didn't see time series in this
This this
model.
is this is this is this is. Can you please repeat the question?
I mean, why they need not use the CNN or something else?
Our ResNet is CNN.
Yeah, I know, but normally LessNet will be combined with CNN, right? But why they implement LSTM? You understand my question?
LSTM. Why did,
Just
yeah, okay. So basically, you want to understand why this is there, because it also updates one second. Yes. So LSTM instead of RNN, that's what you're saying, right?
LSTM is RNN, right?
Yes. No.
It's one of RNN.
One of it. Yes.
Yeah.
Yes. So during the training at one second.
Maybe just my confusion why they still implement LSTM again, because I did not see the reference or mention
Yes.
about
No.
the time
This
series.
is, yes. This is to resolve the problem of, means like it does not resolve the problem of vanishing gradient, but it basically uses, means like if you see here, the previous inputs are still maintained in these layers.
Mm-hmm.
So the gradient degradation, the gradient problem is avoided because of this. Whereas if you use something else, then the gradient problem is not avoided and it might occur. So hence LSTM is used, because it uses, means like as the full form of LSTM is long short-term memory, which is used for avoiding the gradient problem. So hence this is used.
Yes. Oh, this is the definition, right? Of
Yes,
LSTM, why they need LSTM.
yes. But this is the reason why they are using it. Means they could have directly just used the convolutional network and they would have gotten the extraction, means like the values. But if after using this, it also mixes the previous means like the features which are there, because like you said, the time series is not mentioned anywhere. These images are taken at different time,
Mm-hmm.
but the PM value is constant. So which and means like these are taken during the daytime, during nighttime, and actually almost after every minute. So the PM values are kind of similar, but at the same time the features of the image, they keep on changing, which are needed to be maintained to understand the actual means like the values. So hence during the night time also there are slightly different features in the images compared to the daytime, because of the light, the scattering effect, it changes. The scattering effect occurs because of the sunlight, but during the night time the sunlight is not there. At the same time, the variation in the light is there, but only because variation is there, that doesn't mean that the PM value is going to change. The pollution is there.
Mm-hmm.
So to maintain the timeline and different images at different time, the temporal features, the LSTM is used.
Or because they took a picture like in the sequence, right?
Yes, yes. So basically,
That
this particular research is where PM values are not changed a lot, but at the same time, different pictures and different features of the images during different time are considered, and at the same time, it is compared to the same PM value. So hence the better learning and better results occur. LSTM is used to preserve the previous values also.
Mhm. Can you go back to the diagram first? I mean the system diagram. This one. No. The system diagram. That one. So then the use meter also, right?
Yes, for getting the PM values, and also a meter for taking meteorological data to understand these features. How do they affect it? Because here, if we
So
see the sky cover, the UV index, they keep on changing also with time.
so what they need, what they want for the
To make
from
it more,
the image. I mean, which
uh,
feature that they need from the image that they took.
the saturation and the contrast of the
Uh-huh.
images,
Hmm.
those are basically removed. Those are basically taken. But at the same time, these features might change, and they do change at different time. So understanding that becomes a crucial point out here. So hence different, if you see here, the same image is taken at different time, but out here the PM level is kind of constant.
Mm.
Out here the sky covered is different, the UV index is different, precipitation might be there, might not be there, but these features are also taken into consideration, because PM levels, if they are same, the extraction of the features of the features of the image can change because of different time frame of the same image.
Mhm. But the humidity, pressure, UV index, that one is from the meter, right?
Yes, yes, yes.
Okay. Okay.
These are not from
Okay.
the images, but these are there to compare with the images, that during such features also how to go about it.
So they need contrast, right?
Yeah, contrast and saturation.
Okay, ครับ
Okay,
Thank
thank
you
you.
ครับ
So to set up, to check the model performance, images are taken consecutively once every minute across a period of 5 hours per day and over a 10-day period. All images were labeled with the measurements of co-located calibrated sensors. The data was divided into the training set, which is 70%, validation set 10%, and test set 20%. The test set consisting of 613 daytime images and nighttime images was taken during the last 2 days of the 10-day experiment. These results means like the MA is the mean absolute error, SMAPE is the symmetric mean absolute percentage error, R is the Pearson's correlation. These are used to understand the actual, to compare the actual value with the estimated value. Now, like how you asked, if you compare it with the baseline and the previous models, this model actually achieved 6.5% and 6.74% for PM 2.5 and 2.10 reduction in MAE and SMAP value. No, this is only for PM 2.5, and 13.5% and 11.3% for PM 10 estimation. By incorporating the meteorological features, the temperature, humidity, and everything else, the 6 ones, the performance was better, and 24.25 and 20.17% reduction in MAE, SMAPE values for PM 2.5, 28% reduction and 24% reduction in MAE and SMAPE for PM 10 respectively. These are the comparison, this is the comparison chart in which the real measurements, the actual measurements are the blue lines. This is for PM 2.5, this is for PM 2.10, PM 10. And this is the real measurement line. Just the ResNet estimation without using LSTM. This is the line. And by using LSTM, if we see, it is comparable to the blue line. So hence LSTM is used because of the degradation issues, which keeps the previous data also in check. So the limitations and future work are as follows. The deep learning model can learn the most important features that are proxies to the 2.5 and PM10 pollutant concentrations. The estimation performance can still be affected by other pollutants like the O3, NO2 values, which may also degrade the visibility. So in future, the model present on the same methodology can be developed to estimate values of other pollutants such as O3 and NO2 based on sequential time images taken. So like how the meteorological inputs were given, the inputs of O3 and NO2 can also be done in future. Though a large image set labeled with 2.5, PM 2.5 and PM10 measurements has been collected for the study, the range of these values covered remains small. So they are going to actually try and cover a larger demographic to understand, to make it better. The test sets consists of images labeled with low PM values and PM 2.5 values and PM 10 values, which are not available in the training set. So when the training set was taken, the low values were not available to them. So hence, when the images of lower PM values come, it does not do that well. So significant overestimation of PM 2.5 and PM 10 can be observed. Now such overestimations are partially addressed by incorporating one short part at the model structure. Incorporating the limitations and future work again. If the actual PM 2.5 and PM 10 values become too low, less than 10 and less than 20 microgram per meter cube, respectively, the estimation results are comparatively less accurate. Although the short part further reduces the estimation error that associates with low 2.5, the low to PM 2.5 and PM 10 values are large. To overcome this limitation, more images are required to cover a wide range of PM 2.5 and PM 10 values across different time periods and more locations. A large city-based estimation system will be constructed to provide air pollution estimation in those locations where air quality monitoring stations are still not available. Conclusion: an end-to-end ResNet LSTM model has been proposed to estimate PM 2.5 and PM 10 values from smartphone taken images directly. Reliable estimations can be obtained for both daytime and nighttime images. Thank you. I'm sorry for slightly hesitant presentation. I'm a bit nervous.
Sorry. Just
Yes,
my
sir.
comment. I think next time when you make a presentation, you should make your slide easy to understand for the listeners.
Okay.
Because it contains a lot of texts and
Okay.
it's hard to follow. So for me, I am not in the field of machine learning or something on that, so it's a little bit hard to follow as well.
Okay. Can I just go back to the slide and explain it again?
Don't worry. I mean, next time you should try to summarize or digest the slide to be something more.
Because
easier to understand.
I found all these points useful in the presentation.
Yeah.
But that's the thing, because like how Ajan Nathanan, he asked me the question,
Yeah.
like, is this enough or is this like this? These points actually means like which were there on the later slides
Okay.
were kind of useful
Yeah.
for understanding purposes.
Okay.
But yes, I will make it more picturized presentation next time than textual.
Okay.
I have the feeling that it is still difficult to judge whether the proposed method perform well or not, because they use only 10 days. The data was obtained from 10 days. It's too difficult to say that this method is better than that method. It is too difficult. So we should collect the data for different months, like in 1 year. But
no, basically, the research problems in the previous researches that has been tried to address here. And with the less data, which is compared with the other algorithms, this algorithm did better. This particular method did better than the other algorithms. So these images were also fed into the previous algorithms and tried to understand the previous algorithms and the previous methods which have been used to estimate the PM values. Even those methods were fed with the images, the same images. and then comparing everything, all the methods and models, then uh, this was estimated.
Okay.
So 10-day data was also was given and fed to the other models to understand the baselines. So if we see here, one second, just if we see here, limitation, conclusion, results. Compared to the best baselines, the conventional and feature-based machine learning models. So these images were also compared and fed to the other baselines, which and then after comparing the results, these are the results. If we see out here, this has achieved 6.5% reduction compared to the best baseline, and baselines are the other models.
Yeah, and in the future, if you collect the data for a year, maybe it's a good idea to train a model separately for each month, for each season.
Yes,
I
yes, yes,
I think it would give a better result
yes,
than use the all the data to train a single model.
yes,
That that's
yes.
that's my feeling.
Yes.
Okay, so
Means like for different months, different areas also, because there are different types of particulate matters in different areas. There are different types, means like if you're near the beach, if you're near the mountains, if you're on the equatorial line, if you're at, means like different demographics also need different data. So this was particularly done only for the Hong Kong city.
yeah, so I that's good. So I think there's still room to for improvement. Yeah.
Yes, there's plenty room. Means like more collection is needed, more collection of data is needed, more meteorological features are needed to even understand the oxygen levels, the O3 and NO2 levels, not oxygen levels, and other pollutants which might also disturb, and hence the haze estimation will also be proper.
Okay. Uh, is anyone has any more question?
For me, not right now. Got that.
Okay, I will stop the
But
yes.
sir, Ajahn Campbell, what you said was right. It's means like the comparisons have been done with other models. It's just that it has been done over a lesser demographic with lesser data sets. Hello.
Yeah. Um, and any more question? Uh, okay, then I'll stop the recording.
Okay. Thank you.